Thank you very much. Thank you. And welcome back. We are slightly behind the schedule. Let's see how it goes. Yeah, so we had this introductory lecture on graphs. Now we are going to discuss some properties of graph neural networks in a bit more depth. Yeah, let me start by introducing the main ingredients of message passing neural networks. So in the previous lecture, we introduced the general concept, right? So what is the main principles behind graph neural networks? But we haven't really discussed any specific architectures. We just discussed the general principles. Now, what we will do in this lecture, we will first introduce a general framework that's called message passing neural networks, which is known to encompass a vast majority of graph neural networks, right? So many of the graph neural networks are instances of this message passing neural network framework. Okay, how does it work? Well, at every layer, we are essentially updating the node representations in an iterative manner, right? So let's say I'm interested in updating the representation of node I here, that's shown on the slide, right? As we've seen in the previous lecture, we need to rely on the representation of the node that already is available, right? And the representation of the nodes in the neighborhood, in the direct neighborhood of this node. And this is denoted by this notation J in Ni, representing that I'm only picking the nodes J that are in the neighborhood of I, and I'm computing a message for each such pair. And this is why the framework is called message passing neural networks. So a bit more details. So I'm looking at updating the representation of the node I. So I'm computing a message for all J that's in the neighborhood of I. And then I have these vectors, right? Multi-set of vectors that I accumulated from the neighborhood. These are just messages that I computed. I have to somehow put them together. What are my options? I can do, for example, a summation over these vectors. I can do a mean or other kinds of aggregation operators. And so this box here essentially represents the aggregation operator. And then I have a function phi, which takes the resulting vector of the aggregation, the vector of xi, and then computes an update for the next representation of xi. Strictly speaking, I have to actually use time indices here, like superscripts, noting that I'm talking about the representation of xi at time t plus 1, given the representation at time t on the right-hand side. But yeah, for a notational brevity, we are dropping this. But this is an iterative algorithm, right? At every layer, this is the update rule that we will be following. Good. Now, what we would like to discuss now is the expressive power of graph neural networks. Much like the other architectures, the neural network architectures, we are interested in understanding the capacity of neural networks, graph neural networks in this case. Now, the discussion is somewhat more delicate here because we are dealing with graphs, and graphs are more complex than sets, for instance, right? So we need a notion of structural similarity here, and that is given by graph isomorphism. So imagine the graphs that are shown on the slide, on the left and right. So these are essentially isomorphic graphs. What does isomorphism mean? They are structurally identical. It's just they are drawn a little bit differently on the slides, but they are essentially isomorphic. So to make this formal, we say that two graphs, G and G prime, are isomorphic if there exists an edge-preserving bijection from the node set of the graph G to the node set of graph G prime, right? And this means whenever I have an edge between, say, nodes U and V in the source graph G, then after applying the bijection, I must have an edge, a corresponding edge in the target graph G prime, and vice versa. Okay. Now this bijection, of course, does not have to be unique. Yeah. So there might be multiple bijections that witness this isomorphism, because yeah, this is an automorphism group. But yeah, what we care about here is that whether there exists a bijection. And whenever there exists a bijection, we say that the graphs are isomorphic, meaning that they are essentially the same object, there is no reason to map them to different outputs. So our graph neural network must produce the same output when fed these graphs, right? This is the permutation invariance that we discussed in the last lecture. Good. Now, the problem here is that this is a very non-trivial problem, right? So the complexity of graph isomorphism is actually still wide open. It was an open question long time open question. It's a bit of a holy grail of theoretical computer science. It's usually classified as an NP intermediate problem because we of course know it can be solved in NP, but we don't know whether it's NP hard. So it's one of those very natural problems where we don't know exactly where it lies in the complexity hierarchy, right? But we know that it's hard in a certain sense, at least for purpose of machine learning. It's not an easily tractable problem to solve. Good. And of course, we can extend these notions of graph isomorphism to featured graphs, to attributed graphs. The extension is somewhat trivial. So now instead of looking at graphs G and G prime with node and edge sets, we also add a feature matrix to it, right? In this case, X and X prime. And we say that two node attributed graphs, G and G prime, are isomorphic if there exists a bijection that not only satisfies the structure, which is the first criteria, which we have already discussed, right? But also, after applying the bijection on the nodes, matches the features of the original node. This makes sense, right? So if you are going to conclude that two objects are identical, we have to make sure that they are structurally identical, and also the features match, right, through this bijection. This is all that it's saying. So in this case, you can inspect the example. It's still possible to determine by inspecting with an eye, right? So if you just push the gray node a bit down, you start seeing that these look similar. So the bijection in this case is from the green node to the green node, right? From the brown node to the brown node, and so on and so forth. So these are essentially isomorphic nodes, which then yield to isomorphic graphs. Good. So what does this have anything to do with the expressiveness? Why are we discussing, isomorphism and all these things? Well, because we care about the isomorphism classes, right? So for instance, what we would like to do is, of course, we would like to ensure that isomorphic graphs have identical representation. So if I pass it through a graph neural network, a message passing neural network, everything in the, say, red category, which represents all the isomorphic graphs, 3 isomorphic graphs, must be mapped to the same representation. Because they are the same objects, the representation that I produce must be the same. This is the invariance. And the same for the blue category and same for the red category, right? So I'm reducing them to the right representations, basically. But the discussion is a bit more delicate because we also ideally want to have the converse also true. So ideally what we want is whenever they are non-isomorphic, the representations that I produce should be different, even if slightly, right? Because I would like to be able to tell that, okay, these graphs are different from each other, right? This is important, but this is actually not true in message passing neural networks. So what can happen is, as you see in this diagram, say graphs from the blue category and the red category can collapse to the same representation, even though they are non-isomorphic between one another, right? And this is, in a certain way, a loss of expressiveness, okay? And how does this relate to the classical notion of expressive power in neural networks? Because here, in this context, we are discussing about graph distinguishability. Ideally, what we want to do is we want to be able to distinguish all graphs up to isomorphism. This would be amazing. So whenever they are isomorphic, I map them to the same output. Whenever they are non-isomorphic, I map them to distinct outputs. This would be great. Yeah, it would be a complete algorithm on this setup. Now, what happens in reality is that we have a subclass of this, right? Graphs that can be distinguished by message passing neural networks is a strict subclass. It's actually a much, much smaller subclass than all the graphs that are distinguishable by up to isomorphism. Yeah. And what is the implication? If you think about in terms of function approximation, which is what Michael discussed in his lectures, especially the function approximation results given for feed-forward neural networks, MLPs. So what does it imply for message passing neural networks? Well, one direction should be obvious. So when we cannot distinguish two graphs, even though they are non-isomorphic, then we cannot represent functions accurately on those graphs, right? So imagine you would like to do graph classification, and graph classification requires you to be able to tell apart non-isomorphic graphs. So I have two different objects. Imagine I'm doing Boolean classification. I want to map them to different outputs, but I can't even distinguish them. So the representations that I will produce for them is identical, meaning that I will either map both of these graphs to true or 1, or both of them to 0, right? I have no chance of mapping one of them to one class and the other one to the other class. And this is exactly what causes loss of expressive power here. Now, one has to be a bit cautious here because the distinguishability does not immediately transfer to function approximation. So there is a link, because if you cannot distinguish graphs, then you can't do the function approximation that you need to do. This is clear. But just because you do the distinguishability doesn't always mean that you will be able to do function approximation. You need a little bit more. But under some classical assumptions like discrete feature spaces and not requiring some uniformity assumptions, these notions actually coincide. So sometimes they are actually used interchangeably. So this is why we will talk in this lecture about graph distinguishability and try to understand the power of message passing neural networks in terms of their power in distinguishing graphs. And this brings us to a very classical algorithm that Michael also mentioned in the previous lecture, given by these two gentlemen, Ismail and Lehmann. It's a very classical graph isomorphism testing algorithm. It has nothing to do with learning, right? It's just a classical algorithm. And we start with, say, a graph and some initial colors. In this case, and these by colors, I mean, in this case, it's just some kind of code that we start. Let's say all nodes are colored with blue. What this algorithm does is it iteratively recolors the nodes based on its current color and the colors of its neighbors. Very simple algorithm. So, for example, if you are looking at the node that's highlighted in the slide, the kind of update rule I need is I have one blue node, which is itself, and it has two blue neighbors, right? And this is the kind of update I'm getting out of this. And what this means is that the node that you see on the left up corner has 3 blue neighbors, whereas the one on the bottom has 2 blue neighbors. What does this mean? When I compute a new color, I will have to give different colors to these 2 nodes. Simply because this update rule given by phi is given by an injective function. What does this mean? It means whenever I have 2 distinct inputs to an injective function, I get distinct outputs, right? And this is what's satisfied here. And because I have different cardinalities of multisets, I will have to color these nodes differently. So this is what I will get after one iteration. And if I keep on doing this, for example, I can see that the update for the yellow node will look very different from the update to the green node on the bottom, right? Because the yellow node, I mean, first of all, the colors are already different, right? And secondly, their neighborhoods are also different. So if I keep on iterating this, at some point in the iteration of this algorithm, you notice that you reach to a point where the color distribution saturates. So the specific colors that you give don't really matter. It's just an abstraction of what the algorithm does. All that matters is, as we go and iterate over this algorithm, we want to refine more and more, meaning that we want to produce more and more distinct colors. And at some point, this will not happen, right? So after at most n iterations, which if you think n as the number of nodes, we will stop. But usually it can happen, of course, before. So the colors saturate, meaning that even if I keep on iterating, I will not see any new colors. Yeah. So then that's the stopping point. That's the stopping condition of the algorithm. And the final output I get from this is a color histogram. So I see, for example, in this example that 1 purple color, 2 orange colors, and 2 gray colors. This is my color histogram. And if I am interested in comparing 2 graphs, for example, the graph on top and the graph on the bottom, I can run this coloring algorithm on both graphs, right? Extract the histogram from both, and compare whether the color histogram matches or not. That's the intuitive idea. And in this case, the color histogram checks out, and indeed they were isomorphic graphs, and so the algorithm will conclude that they are isomorphic, and correctly so. But it's a very simple algorithm. It's near linear time, the algorithm, very efficient. What does that mean? It means we are probably not solving the graph isomorphism problem, right? Because this cannot be solving this hard problem. In fact, it's a sound algorithm in the sense that whenever it says that two graphs are isomorphic, two graphs are non-isomorphic, this is a correct answer. But when it says two graphs are isomorphic, then we don't know whether it's the correct answer. So it's an incomplete algorithm in this sense. So non-isomorphic graphs that are non-1WL equivalent is shown here. This is the most typical example. On the right, you see a graph that consists of two triangles. And on the left, you see a hexagon, so a 6-cycle, if you wish. They're clearly different, right? So one consists of two disconnected components. The other one has only one connected component. You know, it's different in many, many ways. It's very obvious to our eyes, of course. But this algorithm, this Weisfeiler-Lehmann test, and it's called one-dimensional Weisfeiler-Lehmann test. There are also higher order versions of this test. Cannot distinguish these two graphs. Okay. And let's have a look why. If we take a node, let's say from the graph on the left and from the graph on the right, how does an update look like? For both of them, it's exactly the same, right? So they are both blue nodes. Both of them have two neighbors, both of which are blue, right? So the update in the first iteration that I will get is exactly the same. If you iterate over this, you will notice that this will remain the same throughout iterations, right? So the problem here is that this kind of recoloring is very local and cannot really detect all kinds of differences between two graphs. There are many, many more examples, especially on regular graphs, which are 1WL distinguishable. So these graphs can also not be distinguished by 1WL. Also these ones cannot be distinguished. And in fact, they show up in real world, right? So these are not just synthetic examples. You can see that the counterexamples are not very sophisticated. They are rather simple, right? The ones that we can even distinguish with our eyes, with just a simple inspection. We simply cannot. And in this case, the graph on the left represents a decalin, and on the right, a bicyclopepnyl molecule. I'm hoping I'm pronouncing this correctly. So it also has implications in chemistry and also other domains, this limitation in expressive power. Good, so we kind of get a similar picture to that of message passing neural networks, right? So we had these graphs that would be great to distinguish up to isomorphism, this large class. And now we learned that 1WL cannot do all, clearly not, right? There is a subclass that 1WL can distinguish. Now the obvious question is, given the similarities between the two algorithms, how do the expressive power or the graph distinguishability power of WL test compare to that of message passing neural networks? So that's what we will be looking at next. Let's remember again how these algorithms are defined. So 1WL test is essentially an iterative recoloring algorithm, right? It takes as input the color of the node and the color distribution in the neighborhood, which is given by a multiset. So it looks pretty much the same as the message passing neural network equation that we have discussed, right? It's pretty much the same. The difference here is in the WL test, because it's a classical algorithm, we use an injective function, a hash function, phi, to make sure that whenever the inputs are different, they are mapped to distinct outputs. This is by construction the case. When we look at the message passing neural network, we see two differences. Yes, we still look at the multiset, at the neighbors, the multiset, the features of the neighbors, but we have to choose an aggregation operator, right? So we have to aggregate somehow. So there is no aggregation in the WL test. And two, the function that we use, phi, is a learnable function now. It's some kind of, we need to parameterize it, so we can't just take a hash function there, right? So in this sense, it's kind of easy to see that the message passing neural network's expressive power is upper bounded by 1 WL. And what does that mean? So at best, what we can hope from a message passing neural network is to distinguish the graphs that can be distinguished by 1 WL. So we cannot go beyond 1 WL. And the intuitive reason is 1 WL test in this context does not lose any information. Whenever there is a difference in the multiset of neighbors or in the initial color, because it uses an injective hash function, it will be able to detect it and it will map it to distinct outputs by construction. Whereas for message passing neural network, this is not guaranteed. Maybe we use an aggregation function that just, cannot distinguish between two multisets. And so we may lose something by our choice of aggregation function. Now this brings us to the question of, okay, now we know that it could be at best matching the expressive power of 1 WL, right? But we don't know exactly whereabout it lies. And we said, well, it depends on the aggregation function you choose and other architectural choices we make, yeah? Let's have a look at maybe one choice to make it as expressive as possible. So let's try to make MPNNs as expressive as possible. What can we do? Well, we can look at the aggregation functions, right? So what to choose here? So let's say we have an input that's shown on the left-hand side. So we have the center node. And imagine we are trying to aggregate for the center node. So we are computing messages with respect to the neighbors of this node and aggregating. So the typical choices are max, mean, and sum. So if we take a max operation, this is element-wise. So remember, these colors are essentially node features, right? Vectors. So we do an element-wise max. And this only can capture the skeleton of the multiset. You can imagine many cases where the max will fail to distinguish different multisets. And we will see some examples about this. If you do a mean aggregation, it kind of captures the distribution of the multiset, but it loses the cardinality information. For example, here, I know that for this node that I'm aggregating for, I have 4 green neighbors and 2 blue neighbors, right? But because I'm averaging out, I will only see the distribution. I will see that the weight of green is 2 to 1 against blue, right? That's the only thing I will see. I will lose the cardinality information, the multiplicities, basically. Whereas for some, I can actually preserve all this information. So this, in a certain sense, some could be the maximally expressive aggregation in this context. Yeah, so if you look at some small examples, on the left, you can see that mean and max fails, cases where mean and max fail to distinguish. In the first case, if you take, what do I have as neighbors? I have 2 gray neighbors, right? If I take an average, so it's a mean, it's the same as having 3 gray neighbors or 1 gray neighbor, right? You take a mean, you normalize it with respect to the number of how many grays you have, and so you get the same output regardless of how many gray neighbors you have. So you lose all the information. So the message you compute for the graph on the left and next to it is the same if you use mean aggregation. And the same holds for max. Another example for max is shown in the middle, right? So if I take the max, it doesn't matter whether I have 2 blue or 1 blue neighbor, right? It will do the same operation. It will take the element-wise max between a blue and the green feature. Another example on the right. So this should be clear now from the context. And there is a particular graph neural network called graph isomorphism networks, which has been shown to be maximally expressive within the MPNN expressiveness, right? So, and the theorem statement is as follows. So we assume, I mean, there are certain assumptions that we need to employ. One of them is that we have to assume that the graph node features are from a countable set. And then we assume that a message passing neural network has an injective aggregation function. So this is usually a function combined with a sum aggregation. We need an injective update function and graph bias readout. So the pooling function that we use at the end must also be injective. So if we can make sure that all components are injective, because composition of injective functions are injective, the result of the aggregation will be injective, right? And this is what we wanted to achieve anyway. So this was what we were lacking in when compared to the WL test anyway, right? So intuitively, this is the idea. Of course, these assumptions may be a bit unrealistic in the real world, so we need discrete countable features, which doesn't necessarily hold. But the rest of the proof is very similar to what one does in deep sets. So essentially, we are decomposing in a similar way to deep sets and showing that we can define an injective function that decomposes into sum of terms, and use this observation to also show that this update rule in graph neural networks can be made injective. So the proof goes, very high level idea of the proof is to show that it's possible to have such an injective functions, and then use an MLP to say that, okay, I have these injective functions, I can represent the composition of these injective functions with an MLP. Why? MLP is a universal function approximator. I can approximate these injective functions using an MLP. There are more details about this and points that one has to be careful about, but this is the very, very high level idea. So in this case, what we see is actually graph isomorphism networks and also other graph neural networks, there are many others actually, can match the expressive power of the WL test, one-dimensional WL test, I must say. Yeah. Still a subclass, of course, a small subclass of all graphs that are distinguishable up to isomorphism, but at least now we know which ones can match the power of 1WL. Good. Are there questions so far? Because the next lecture will be about designing even more expressive graph neural networks, which go beyond the power of message passing neural networks, and it will get substantially more involved.
First, two times of so my question is very basic, but you talked about one WL test, and in that you took a particular node for color segregation, right?
Sorry? The last part I didn't get.
You used to select a particular node for color segregation.
I choose what? Can you repeat that?
A particular node for color segregation, one by one. You used to select a particular node.
Right, yeah.
And what if we have higher dimensions? Like, what if we have KWL rule and we use that to select?
Right. So that's the topic of the next lecture. So yeah, there's a lecture dedicated to that. So yes, that's one way of going beyond the expressive power of 1WL.
We select tuple or set for that?
Yes.
Calling multiple nodes.
It's not about calling multiple nodes, but so basically you will be, instead of coloring single nodes, right, you will be working with k tuples of nodes, and yeah, that's the fundamental idea.
Thanks.
Yeah, thank you.
Excuse me, sir. So in case of the aggregator function, if we assume that suppose the set of colors that we have is a countable one, and we decide to have primes to the power of the number of that color, won't that be a unique aggregator as well, without using any?
So you're saying, can we have unbounded feature domains and then somehow encode this with prime encodings? Yeah. So there are encodings as such, but the construction is a bit more complicated than that, because one has to be careful about what assumptions we use and what claims we make, right? So if you don't assume uniformity, it's a different question. So do we allow, for example, a different construction for every graph? So that's because that prime encoding might require that, right? And do we assume some upper bound on the graph sizes, for example? If not, then you're dealing with very large graphs, unbounded. So then some of the constructions that's at least presented in the graph isomorphism network paper break. But yes, it's possible to extend the result to unbounded domains. Yeah. If there are no other questions, I can move on to the second lecture. Yeah.